Good. So, yeah, I just finished 2 papers just last week, and we'll be talking about them. And now at the unusual time because we have the department meeting at astronomy at 2 o'clock. Everybody's welcome to.
It's welcome, but not required, right?
Not required, but
nice
as a
cake.
benefit, you get
They give
free
cake or
coffee
buns or
and
something.
maybe some proper cake.
Proper cake. So I'll start. So actually, this paper is one of the longest paper I have ever written in my life, and this actually took a lot of time. I think we were working on this paper for last eight months. That was also one of the longest times. But surprisingly, when I prepared the presentation, I found that there were not as many slides as the amount of work was. So.
That just means that you successfully winnowed down all the details and extracted the essence.
Yes, maybe yes. Or it may be that I was preparing the talk in just one day. That may also be the reason. So, should we wait for Dhruva or will start? So this is the setup. So simulation is a Cartesian one, but with gravity pointing in the negative z direction, and with respect to sphere and the direction of rotation, you can see that you can place the box at any co-latitude theta, so that omega makes an angle theta with the vertical. And then we have, so the box is of dimensions Lx, Ly and Lz, where Ly is the longest dimension. So typically Ly is something like 3 or 4 times the size of both Lx and Lz. And the gas in the box is stably stratified with a polytropic index n is equal to 3, which means the capital gamma is actually 1 plus 1 by m, so which is like something like 4 by 3. And then there is a magnetic layer somewhere near the bottom of the box, but not quite at the bottom. And this layer has a thickness which is something like 10% of the total height of the box. And then, so this is the initial condition for B. So there's a B is only present in a horizontal layer and it points in the direction of the longest dimension of the box. So you can look upon By as being the toroidal field if you look at this geometry. And initially all Bx and Bz is completely 0. And we only have for initial condition for U some randomly placed horizontal eddies. And there may or may not exist a random vertical velocity in the box, which is very small. I mean, these eddies have typically Mach numbers of around 10 raised to minus 5 or so to start with.
Can I ask you a question?
Sure.
So, why do you use both the adiabatic?
So that it's subadiabatic. It's strongly subadiabatic, and it's whatever I do, I do not excite convection in the box. That is the reason. I mean, I don't want convection in the box because I want to study this in a stably stratified. So m is equal to 1.5 would be the point where the things will become unstable to convection.
But so you looking at the picture, the box looks pretty.
The box looks because I could not stretch it in that direction.
But like the curvature, so the box is compared to.
Yeah, so box is like.
It's very small compared to the.
Yeah, so if you look at, I mean.
That's what you imagine if you take the radius of that thing to be very.
Yeah, so this is, I mean, basically the box should probably look like this. So this, I mean, this is something like 3 times, and then this is 1 and 1. So the aspect ratio is 1:2.
Okay. Now I mean like compare like to the curvature. You don't have
no, this is a Cartesian simulation, so I'm just showing that since we have rotations, I'm just showing that these are the transformation from the Cartesian coordinate to the spherical one, but actually this is a Cartesian simulation. But since it also has rotation, I'm trying to show that this is the co-latitude, or the angle between the vertical and the rotation.
Regarding polytropic indices, maybe we should just write down the capital gamma is equal to 1 plus 1 over n. And
Yeah.
so you have little n is equal to 3.
So it is like 1 plus. Yeah, that is what I was telling you.
So it's 4 plus n.
And you use
And
ideal.
capital gamma is this.
And so you use ideal gas equation instead, right?
What's
The
the difference
polytropic,
between capital
ideal-
and small gamma?
Small gamma is actually the adiabatic index. I mean, for example, suppose the gas were adiabatic, then the relation would be this.
So capital gamma is for the stratification, and little gamma is how the gas behaves.
If it were adiabatic. So that is always 5/3 for an ideal monoatomic gas. Okay, and then so what we are trying to study is the buoyancy instability. So I told you initially that there was a magnetic layer somewhere here. So this is the bottom of the box, and this is the z direction. And what happens? I mean, when we have a magnetic layer in this region, the density of the gas also reduces because the magnetic field exerts magnetic pressure corresponding to B square. And now since the density here decreases, the whole layer is actually buoyant. And then the whole thing becomes unstable, and then these are basically the density fluctuations that you see here. And you see that there are these rising tubular structures here, and all of these have negative density fluctuations, and hence they are rising.
So the field is
Field is like this, out of the box, out of the plane of this fluid. And then these are these tubes. So I mean, this is just to show that this is indeed a buoyancy-driven instability because it's driven by
so
this.
what sets the mode of the instability? This is Kelvin elements.
No, this is not
No,
Kelvin.
sorry,
We don't have shear.
related or like.
Yes, I mean more like what do you say, Parker's? Parker's instability. Or
So,
something.
but
It's just the-
It's,
I mean, it's just that the density in the magnetic layer is lower
yeah.
than the surrounding, and it is.
No, but I was wondering if you had 1, 2, 3, 4, 5, 6, 8.
Oh, you said you are talking about the mode.
Yes.
Oh, that mode. I mean, okay. Then in this context, there are actually two kinds of instabilities. One is the three-dimensional instability, and one is the two-dimensional instability. So the two-dimensional instability is the one in which I just have a layer here, and then this when it breaks up into tubes, there is no. I mean, ky is always equal to 0. So I mean, they break up into modes like this, but this is always 0. Whereas the instability that I'm studying, I mean, this is completely 2D because you can neglect one dimension. Whereas the instability I'm studying here is different because in that case,
But you cannot decompose in normal mode.
yes, of course we can in the linear state.
Okay, so the growth rate is independent of the two modes, right?
What two modes? No, this is a completely different instability. This is a 2D instability, and what we are studying here is a 3D one in which these tubes are actually like this. Initially. So they do this. This is their natural.
Initially in the linear phase.
In the linear phase. So
Yeah,
this is the mode which is excited. So this is the instability that we are studying and not the 2D one. And these two instabilities have different what do you say, conditions for being destabilized.
So that is the
You are
2D
asking
one.
why it is 9 or why it is 8 and
Yes.
why do you see? That I don't know. That is the mode which is excited.
It's because of the
In the
initial
linear
condition,
phase.
maybe, of the velocity.
No, it is not because I don't think it is because of the initial.
I mean, this depends on the Prandtl numbers, for example.
That may depend on that. Yes, because that I
And
showed.
there's a linear theory which we made reference to.
So, but if I do a cut like this
Hmm.
in the linear phase,
You will see-
I should see the 2D move, right?
Provided the condition for the 2D mode is also satisfied in this box, that I have not checked. But I'm saying that initially when I look at the linear mode, it always looked like this.
So
So, for example, I can show you. I don't have it here, but
In a cross section, of course, it will look similar to the other modes, but I don't think you can necessarily say that you have two sensibilities going on at the same time. They may, but
yeah, for example, this figure here.
Yeah.
So this is the velocity in the linear phase. So this is again in the xz plane. So you see that this is something like 8 or 9 here, and in the y you see that this is
okay.
one mode here. So this is the 3D instability which is getting excited actually.
And the other thing I was started on the whiteboard, we can point this out. The initial profiles
Oh,
of
yes,
temperature,
right.
pressure, and density are such that the density is actually not perturbed by the magnetic field. But the gas pressure, of course, has to be perturbed or has to be lowered because magnetic pressure contributes to total pressure equilibrium.
They are all linear. It decreases.
No, maybe I should write logarithm.
No, they have a
This logarithm.
Temperature is linear.
temperature
Is the
is
logarithm-
linear. These are not
The
density and
logarithm is
pressure. But I mean, it has been adjusted such that the hydrostatic equilibrium is still obeyed. So if there were no velocity, so velocity, if I put the velocity to 0, then I mean nothing should typically get done.
So this,
Unless there is some
you mean that
numerical.
So the
noise.
density is not perturbed.
Density is not perturbed. Not perturbed as in not changed in the initial stage. So we have an initial background and then we put a magnetic field, but that means that the initial polytropic background has to be modified if you still want the hydrostatic equilibrium to be
Yeah, so there is a dip in
Right.
the pressure
So
doesn't
we-
satisfy the
So we
polytropic
modify
Okay.
the initial pressure. I mean, since Penzico doesn't have pressure, we modify the sound speed and the entropy, and we keep the density constant so that the magnetohydrostatic equilibrium is still
So this is
restored.
not,
It is unstable. It is an unstable equilibrium, but it is still an equilibrium.
So this is not due to the fact that the flux field has less mass and it buoyants up.
Only secondary, only later.
Only later, because it is unstable.
but the number of
Modes.
modes is depends on
think
what?
I think aspect ratio can also play a role, because I mean I would think aspect ratio would play a role, and also the viscosity and the heat conductivity and the magnetic diffusivity can also play a role.
And of course, it's actually in the presence of angular velocity, rotation.
Yes, and there is rotation, of course, but I'm not sure how that, because I have not checked whether these numbers are preserved for different rotation.
And this was no.
But I think aspect ratio is also.
And you have not excited the move. You don't excite the move by hand.
No.
You have no seeds essentially. You let the simulation just
No,
run.
Just a
just-
seed. You said
Seed as in there is this random eddies, but not of this
Okay,
M and
there's a random white
there's a
noise.
random, but then the mode selects whatever initial condition.
That's why I say that the random eddies should determine the number of.
I mean, it's also the fact that the layer, the magnetic layer is 1/10 of the box size, and this is about K of n. So you're saying that the width of each rising thing here is about the same as the width of the initial magnetic layer.
Not necessarily.
No, I think it is the aspect. The aspect ratio is really more important. That is my hunch, but I have not checked that.
Short question. The temperature, density, and pressure that are drawn there in function of Z.
This is a function of Z, yeah.
Yeah, but so is the central layer this equation is equal to
Yes, initially it does, because the magnetic layer
Just
is
initially.
constant in X and Y, right?
yeah, no, okay, but
So
doesn't state it.
The polytropic.
This equation.
Yeah.
No, this equation wouldn't work anymore in that region, because we have modified it. This is only applicable in the polytropic. Right? I think it's polytropic in absence of any magnetic. Yeah, so now we have more or less all the I mean, we have rotation, we have magnetic fields. So then we can wonder that why is it that how is this instability different from the MRI that people studying the disk? So I was discussing that with Matthias and Dhruva yesterday, and we put down some points. That is, for buoyancy instability, the stratification and compressibility is an important thing because the density has to change for it to rise. And then, whereas for MRI, you don't need stratification or compressibility. For this buoyancy instability, rotation and shear are not required, but they modify this instability in a certain way. Whereas differential rotation is very important for MRI. I mean, this is one of the necessary conditions for MRI, and also, of course, in presence of magnetic fields. And whereas for the buoyancy instability, you need, I mean, one of the necessary condition is that the thickness of the magnetic layer has to be much less than the typical scale heights in the box. So if you take any of this, especially the density scale height, now since these are polytropic, everything is related. So typically the magnetic layer is much thinner than the density scale height in the problem, then this instability is easily excited. This is one of the necessary conditions for the instability.
Actually, Kelvin, so that density plot in the top there, is that actually right? Is that what you have? The row?
Row will have typically, I mean, what? I think it's probably.
Because that means you don't have any gravitational potential energy.
No, this is
So
this
the
row
energy
will look
source
linear.
is the magnetic field.
So it's probably an LM row. It's LM row as well. But if you look at potential energy,
No, why not? If you solve,
potential energy.
no, if you solve the hydrostatic equation, constant gravity, and then you also take into account that this is this dependence and also this, then you get such a, it may not be exactly like that, but this is what you have. If you solve these three equations.
In this case, to have this bump, you need to have the magnetic field there, or no?
That is later on. First you get the background state, then you modify it. But you have not changed the density, you have only changed the sound speed and the entropy.
But the background has this bump?
Background doesn't have the bump.
Okay, so that's
It's a
what
perturbation.
That's
After you
the
put it
perturbation due to the
adjustment
magnetic
after putting it in the
So,
field.
but how do you treat rotation here?
You are in the rotating frame, right?
Yes, but there is only Coriolis force, no centrifugal force.
But not even in the equilibrium?
But
I mean, the density, so the PDR, it's... Okay.
So one cannot, in a periodic box, it's certainly possible to put the centrifugal forces. They, of course, will only modify the gravitational force.
the gravity essentially, yeah. But that we have not taken into account.
But in your second point here, say rotation and shear are not required, yes. But does the rotation affect the growth rate?
Rotation affects the growth rate.
Yes. So they're not required for the instability.
But they modify the
I
instability.
see.
That is what I
It's not
said,
the
that
gravity.
it modifies the instability, but it's not paramount to its existence itself. Okay. So here I have shown an advanced snapshot in time of the By, which I shall call the toroidal field from now onwards, in the xz plane. So x is the shorter dimension here. So I think this is somewhere in the middle of this box, so in this plane somewhere. And in the same plane, this is the current helicity that has been shown. And these vectors are actually the velocity vectors. So this is actually, this box has been placed in the northern hemisphere, and due to the effect of the Coriolis force, you can see that these tubes are rising in a way so that they are tilted towards the right. And if you place the box in the southern hemisphere, they will go the other way. And also, I mean, there are these high kinetic helicities as well. at the top of these tubes which are rising to the surface of the box. So, I mean, this is important because initially we didn't start with any current helicity in the box because we just had By, which had a gradient, but then there were no other magnetic fields. The initial current helicity was 0, but then we ended up developing a lot of current helicity. But from this simulation, I cannot say that whether the current helicity is preferably negative or positive, depending on the sign of omega. That I cannot say from this.
You know what it is. It's negative. Actually, it's
I have not calculated the total one. The volume of the one. This is both signs here, so this little. I mean, cannot say this from the plot. I have not calculated the.
So, I mean, there's some form of inclination in this feature.
Yes, that is the effect of the Coriolis force.
It depends on the angle of the rotation.
Yes, yes. Yeah. So in the northern hemisphere, it will be this way, and southern it is the other way. So, and this is actually the volume rendering of the surface. I think it is probably the, say, the half. I mean, suppose I start with a particular magnitude of the field, which is B naught. So this surface is somewhere around half B naught at an advanced time. And then these are actually for different Prandtl numbers and magnetic Prandtl numbers. And this is interesting because for a particular relation between the Prandtl number and magnetic Prandtl number, we found that these tubes, even though they break up from the magnetic layer, but they don't develop any visible twist. So that you can see in the volume rendering as well as in these field lines here.
Which program you use to?
This one is MATLAB. This one is this
Paraview.
Paraview. So and this one is for another case where the ratio between the Prandtl number and magnetic Prandtl number is small. So this is somewhere around 0.25 if you take the ratio of these two. And here the ratio is actually 1. So if you decrease the ratio between the Prandtl number and magnetic Prandtl number, it appears that the tubes that are developing from this magnetic layer have considerable amount of twist. So,
What are the colors to the right?
oh, these colors are basically the magnitude of the field. So this is volume rendering at a particular magnitude, whereas these are field lines and they are colored according to the value of the toroidal field or the By.
So left is isosurfaces.
These are isosurfaces. So and then this ratio of the Prandtl number and magnetic Prandtl number is called as the I mean, it's basically the inverse of the Roberts number, and the Roberts number is defined by the ratio of the molecular magnetic diffusivity to the temperature conductivity that appears in the entropy equation. So what does this mean? So then I have done many runs. So this is again the inverse of the Roberts number. So basically it is this k divided by eta here. So as the k
Increase.
phases, no, wait, then it is
Roberts minus 1. You're calling Roberts minus
no,
1.
this is correct.
Yes.
But maybe there I have written it.
Oh,
because this is supposed to be that here. I mean,
yeah, but I think it's
the
correct.
k is supposed to be larger in this region, which means that eta is smaller. So this is actually eta by k. So it is Robert number inverse is eta by k, not the Roberts number. So what happens here is for very efficient heat conduction compared to the magnetic diffusion, the growth rate of the instability as well as the twist parameter that this is epsilon j, some twist parameter that we calculate, is much higher compared to the runs where the heat conduction was inefficient compared to the magnetic diffusion. So this means that this means that this equation is one of the necessary and sufficient conditions for this instability. What this means is that the this is basically the ratio of the magnetic not scale height, the thickness of the magnetic layer to the density scale height, and then you add this stratification dependent term here. So in presence of higher heat conductivity to diffusivity ratio, so higher K by eta, this term decreases by the same factor. And so, I mean, in subadiabatic stratification, this term will try to be positive, so this condition will never be satisfied. So, but if you have higher heat conduction, then this term, the effect of this term will decrease, and then this condition can be easily satisfied even if you have subadiabatic stratification. So that's the
circles of different diameter.
sorry.
These different circles.
Oh, different circles are the sizes are actually at different for different Reynolds number in the run, and because we took the ratio of the magnetic to magnetic diffusivity to heat conduction, we lost the information about the viscosity. So we put the Reynolds number in terms of these sizes here. So bigger ones are at higher Reynolds number, and smaller one smaller Reynolds number, the fluid Reynolds number, not the magnetic Reynolds number. So this is what I was saying, that the last term stabilizes the buoyancy instability in presence of subadiabatic stratification, but then this factor is reduced. This term is reduced by this factor, and then you can easily have instability. So that may be the reason that we observe this, but earlier nobody had systematically.
What is that?
This is the growth rate. I mean, the growth rate which has been non-dimensionalized by the Alfvén travel time in the box
And
in the y direction. And this
epsilon?
is kind of a twist parameter, which is basically this. So now, what happens in the during the time evolution is that we have this magnetic layer initially, and then it basically starts spreading at a particular time, and as it does so, other magnetic field components also develop. For example, we started with a By, and then we ended up Bx, ended up having a Bx as well. And this you can see here that this is the time evolution for, I mean, this has different runs, but this time evolution typically has two phases and with different decay rates. So it decays here and then it decays faster here. And the growth of this magnetic field component, that it just exponentially grows from 0 and then it reaches a saturation, but then on a logarithmic plot you cannot see that, but then it again decays very slowly, because there is nothing to sustain the instability. And what the velocity does is this. So initially, since the stratification is stable, so the velocity excites these G modes, and then you can see these Brunt-Weisser oscillations here. And then this velocity also exponentially grows, and then again it decays with a very slow decay rate. So all these components here are actually horizontal averages, and then we call them the mean fields. So, and then I mean there are different runs for different Prandtl numbers and everything. Okay, so yeah. So an important thing is that we start with only one component of By and we end up with other components. This means that there must be some transport coefficients like alpha and eta which can be calculated from this problem. And maybe under suitable conditions, this can also be an important dynamo mechanism for in the stellar context, for example. So then we made an elaborate effort to measure this alpha using what is called as the quasi-kinematic test field method, which is basically the in the pencil code, which is basically the test field underscore z module. But this problem is different from the usual calculation of alpha from convection or from forcing that is carried out, because of the following reasons. One is that the turbulence is inhomogeneous, because we started with a very localized layer of magnetic field, and this might mean that the alpha that we calculate is non-local in space, and also this turbulence is not really stationary in time, because it exponentially grows to saturation and then it gradually decays. So there is non-stationarity in time as well, and then memory effects may be important. So this effect is actually both non-local in space as well as time. But just for simplicity, we have ignored the time, the memory effect, and we will only concentrate on the non-locality in space. But then the most important question is, does the test field method work in this problem? Who knows? But there is a method. What we do is we can reconstruct the EMF. I mean, you know that the EMF is given by, the EMF is this. And this is also given by right. So if these two equations are equivalent, and we know this from the simulation because we can easily calculate this by horizontal averaging the correlations between fluctuations in velocity and magnetic field. And we can also reconstruct this EMF because we can calculate alpha and eta from the quasi-kinematic test field, we shall call it QKTF.
The eta is the turbulent eta or the turbulent eta?
This is the turbulent eta. The EMF is the turbulent eta.
Also tensor.
Also tensor. So now since this is a three-dimensional thing, so this alpha will actually have, it actually should have 9 components, but since we have defined our averages like xy averages, so the z component is not important. So, and similarly eta will have eta 1, 1, and then all these components here. So in these tensors, what is important? I mean, initially if you start with a By and it generates Bx, then we have to especially look at these two components, alpha 22 as well as eta 22. But then we still look at the entire tensor. Okay, so now back to this reconstruction things. So we can calculate these tensors from the test field method, and then we can multiply them by the mean fields, and then we can see if we get this EMF or not. So we did the simplest thing. We used just the linear test fields. So I'm not actually discussing what is the test field method in this talk. But what we can do is we can use test fields are basically like test charges which can be used to probe the electric field, or in this case the EMF. So, and for problems of this kind which are three-dimensional and we calculate means by horizontal averaging, we actually need a pair of 4 test fields. So as in, I mean, so suppose we have linear test field which is like it goes as 0, 0, 1, and then we have another one which like goes 0, 0, z, and then
Not the Z component.
huh?
The X
No,
component.
sorry, not x component. Sorry, let's say first it is 1 here, z here, and then this is 1, 0, 0, and this is z, 0, 0. So this is the simplest test field that is incorporated in the pencil
It's like
code.
a 2. It's
get the alpha and eta from this, and we multiply it by the mean field that we get from this model. And then we compare this, and we find that they're absolutely off. They just don't agree with each other. So then what do? Then we do such a complicated thing. So we look for we look for modes, the Fourier modes of the actual mean field in the box.
So, I mean, what you did in the first step was simply just ignoring the fact that there's a convolution, you were just using multiplication,
Yes.
assuming that the kernel is a delta function.
Yes. Right, I should say that, yeah. So, I mean, there was no convolution, so it was just straightforward multiplication. So, instead of these zeros here, you just have a simple multiplication. So, then that doesn't give the correct EMF. So, now we have to think about the right definition of alpha, which is convoluted in space. So, what we do is we break up the the mean magnetic field into its Fourier modes. And we find that there can be two groups of modes, one sine modes and one cosine modes, like these here, both of which satisfy boundary conditions and they have different wave numbers. And then we can break up what we should do is we should break up this EMF into, this is not quite a kernel but something like a kernel or a transfer function into the Fourier component of that field, not the entire mean field but only the Fourier projection of that field. So if we make up if we add up this whole thing so that convolution is complete, so now our job is to compare such a reconstruction with the actual EMF. But before that, we also have to look at the convergence properties of these alphas and etas, which have been calculated for different wave numbers. So, I mean, we can change the wave numbers of the test field, and then we can calculate alpha and eta for that particular wave number. So, if we do that, so you can see that suppose alpha 2 component of the tensor, and this is actually the wave number which is increasing. So this looks like this is converging here, or at least going to some steady value, whereas the off-diagonal components don't converge as you increase the wave number.
Maybe converge is not the right term actually, because there's no requirement. If you really had a multiplication in grid space, that would correspond to a constant in Fourier space. So if the numbers were constant in wave number space, then that would exactly mean that we could have a perfect multiplication. We don't need convolution.
Yeah.
Only if they change this k.
Yes, but here they don't change with k. So I mean.
Yes. Yeah, that's not bad. I mean, that's just.
Yeah. So I mean.
It's not. I mean, convergence sounds like if they don't go to zero, there's something wrong. That's not the case. Because think of the simplest case of the constant read space.
Yes, I mean this only requires that the field has to converge with k and not the coefficients.
So these both are the Fourier transform of the
No, this is not the Fourier transform. This is the alpha, which has alpha and eta calculated from the test field method, but using different wave numbers for the test field. So now the test fields actually look like this.
I mean, it's just still the Fourier transform of the alpha kernel with respect to the second argument.
So now look at say cos k z.
I should explain one thing first. So normally, if the thing is translation invariant, you can write alpha as a function of z minus z prime, right? If it's not a translation invariant, you have to write z comma z prime. However, a much smarter method is to write this one. It's completely equivalent of writing alpha as a function of z and then z minus z prime. That can still be done, and it's physically speaking much more meaningful than. Because this then indicates that you have still local interactions. When the distances are not too big, you have local interactions. And now from this,
then we take the Fourier transform with respect to one coordinate.
Yes. So then she has Fourier transform in this respect.
Okay, so this is it's basically the Fourier transforming wave space over the kernel, if you want, the kernel radius of something like that.
Yes,
of
exactly.
of-
Yes.
Okay. So, but
Yes.
why? So it's equal to 0 for high k, right? Or
Yes.
No, as Axel was saying that it need not go to 0, but it should reach a constant level at least. Which means that, look, if you try to reconstruct your B in terms of the Fourier modes, what happens? That you can truncate it after a certain point, right? At a certain k critical or k max, you can truncate it. So which means that modes higher than that are not important. So if this alpha remains constant, then you can also truncate the EMF at that same k max. Because alphas are constant and the B's are going decreasing.
What,
So the
what if alpha is a delta in the second argument?
Alpha
Alpha
is
is
a
a delta in the second argument.
Yes.
Then if you do an FFT on the second argument, we have lots of power at very high note.
No, it's a constant.
It's a constant.
the Fourier transform of a delta is a constant.
And of course, you can then still truncate because you would only multiply with the B field. And the B field itself doesn't have much power on the very short scales typically, and that's why. Why it's okay to.
This works. This still works even though
So do you know why
it doesn't go to 0.
that you still have power at very low k?
At very low k.
Yes.
Uh,
K0 you have lots of power, which seems strange. Like you have an infinite.
That just means
No,
that how the
that-
constant field will go.
that means that
That's alpha for a constant field.
I mean, it really means that the alpha effect works best if the field is as smooth as possible.
Oh, okay.
And the more corrugated the field is, the less efficient are these transport coefficients.
yeah, but for some time, I mean, they are initially flat, for example, here, and then they start decreasing. So, I mean, for example, linear as well as the first harmonic has the same power. So,
By comparison with this isotropic homogeneous turbulence, one thing we know already is that we have such a form, but then it's in wave number space to these diagonal composite, alpha 2, 2. Alpha 1, 1 is
I have not shown
Alpha
alpha
not
1
yet.
1 here.
They behave like Lorentzians in wave number space. And then the functional form is exactly 1 divided by 1 plus k divided by kf squared. And kf is the wave number of the energy carrying gates. So that's what we should compare against. And then this one is 0, for example, for isotropic turbulence. So therefore it's not surprising that it's also not very big for 0 again. And this is again like it should be like a Lorentzian if it's isotropic.
Yeah, for isotropic turbulence it's 0, but then this again grows for.
Yes, yes.
But the behavior is opposite for the alpha, the other off diagonal component. So you should not.
The solid line is gamma.
Solid line is the gamma, which is basically you can convert these off diagonal elements. I mean, you can define a gamma, which is the pumping velocity, using this formula here. This pumping velocity is directed in the. I always forget this 2 1 and 1 2. But basically a difference of these two things. And then that pumping velocity is higher for even for homogeneous fields. Even though alpha 1 2 is not. Yeah, so this is about the reconstruction of the EMF, and the EMF now has two components, only EX and EY. And then this is the real EMF from using that U prime cross B prime, the real EY. And then this is the reconstruction using modes up to K prime is equal to 16. And the last panel is only using the lowest harmonic, which is K prime is equal to 0.5, so which means there's a half wave in the box. So this is completely off, opposite in sign, but this EMF is, I think, not that bad. The EY is not that bad, but EX is quite bad for the first harmonic. So then how do we quantify how good these fields are? So for this we have defined two things. One is something like a error, the relative error, and then the other something like a correlation function. So this error behaves in a, I mean this solid one is for Ey and this dashed one is for Ex. So you can see that there's a dip here and then it maximizes, but that this may be because we have very small resolutions and we have used something like 64 cubes. So we really don't know whether we should, I mean, this dip should come here or somewhere else. But from this figure, it looks like it doesn't improve the fit if we take modes higher than k prime is equal to 8, for example. On the other hand, the correlation function is quite good. So that reaches something like 0.98 for the Ey and 0.95 or even 0.9 for Ex. The correlation is quite good, but the errors are a little higher. But I think still it's quite good. So this is an important result in the paper because we have illustrated a simple method to test whether this quasi-kinematic test field method really works for inhomogeneous problems or not. Okay, and this is another interesting thing. So what happens if the initial field in the layer changes? That is, in the case of stars, and we can say that what happens if we change the plasma beta in the, for example, if you have a strong magnetic layer, what happens to the alpha that is generated due to this layer? So what we found is, this is something like a square root of the plasma beta, the initial plasma beta, which is, you can say this is like the increasing magnetic field here, and these are the alpha coefficients, and then these are the, this is only one component of eta, which is eta 22, and we see that for most, I mean, we have actually not explored a very wide range, and our plasma betas are actually quite close to, I mean, around of the order of 1 actually in most simulations. So it's not a very wide range, but still you see that the alpha effect actually increases with the magnetic field. So this actually, I mean, is something called as anti-quenching, and such a possible observational evidence for this was presented in Brandenburg et al., where they compared the cycle frequency, the magnetic cycle frequency in the stars with their rotational. So basically, they looked at this ratio. I think this was lost. And then there were, I think, 2 lines like this, right?
Yes.
And then I think one could go from here to here or something. And then I mean, this could be presented by very simple models where actually you need alpha to, we say alpha 0 into some d raised to some p, where p is actually greater than 0 rather than less than 0, which we see in ordinary problems. So this actually can make this alpha from buoyancy instability an attractive candidate for solar dynamo models because first of all, that alpha won't be quenched by strong magnetic fields if they are present at the bottom of the convection zone. And then what else? Yes. Now what we do is, if this is important in the solar context, how does this alpha behave as a function of the latitude? So instead of doing a spherical simulation, all we did was we make the box travel from the one pole to another pole. And then we calculated our results. So we found that the growth rate is actually highest at the poles and it decreases monotonically as we approach the equator. And that is presumably because this buoyancy instability depends crucially on vertical motions. And what the Coriolis force does is it bends this vertical motions to become horizontal ones. And this effect of Coriolis force on the vertical motion is strongest at the equator. And hence this instability is, the Coriolis force suppresses this instability near the equator compared to the poles. So this was also actually proposed by Schmidt, and then so then what we have done is we have made the box travel from the north pole to the south pole, and then we have calculated the magnetic. We have just shown the magnetic field here, but what is striking is that the Bx, which is generated from this By here, is actually non-zero near the equator. So in the traditional alpha effect, you would expect, since alpha is a pseudo-scalar quantity, when you go from northern hemisphere to southern hemisphere, it should change sign. And if it changes sign, it means that there must be a place, which is the equator, at which it goes through zero. But it doesn't happen here. But
What decided the polarity of the field?
this was always the same polarity.
Yeah, but the one above.
That's
That's the generated field. So blue means negative and red means positive.
And on the equator you have
Equator
red inside and blue outside, right?
Yeah.
So why don't you have the other way?
We can have the other way around if we change the sign of By, for example. That is because the alpha effect will have a certain sign, right? So it should depend on the sign of the alpha effect.
No, this is also not symmetry breaking.
No. Now we have not come to symmetry breaking.
But I think it's probably still the same reason. So if
It's
you-
still the same reason, but what I'm trying to say is, in all these calculations, we have actually used the initial velocity field, which is the same. So that has the same kinetic helicity, and then
I
we
mean,
get
small
such a
perturbation.
result.
It has a small perturbation.
Very small perturbation in helicity,
That
but
actually
it's
goes.
the same for at all the latitudes. So then this may not be the correct way of calculation. The correct way would be to reflect the initial velocity field, so that eddies in the northern hemisphere, clockwise eddies start looking like counterclockwise eddies in the southern hemisphere, and then do the calculation. So if we do that, then we don't quite get this. I'll tell you how we have got this. There's a little bit of trick here, because what we have done to produce this picture is that suppose u is the original initial velocity field and ur is the reflected one. So clockwise eddies become counterclockwise and upward velocity become downward velocity. With this, we calculate with this initial condition, we will calculate an alpha. With ur, we can also calculate an ur at each latitude. Right? And when we do that, an average, we get such a plot here. And there are certain symmetry relations between alpha and alpha r, and those are that alpha at a particular positive latitude is actually equal to alpha reflected with a negative sign at the negative latitude, whereas the off-diagonal components, they don't invert in sign here. But we cannot just have the original velocity and the reflected velocity here and get a non-zero value for alpha here, because what happens at 90 degrees is something very strange. So depending on the so how do you decide what initial condition to take at the equator? Should you take clockwise eddies or anti-clockwise eddies? Suppose you start with clockwise eddies, you end up getting, say, a positive alpha effect. And then you do the same simulation with anti-clockwise eddies, you get a negative alpha effect. So alpha effect, the alpha is still non-zero, but when you add them, that gives the zero. So I mean, we have actually done this trick to produce such a thing here. But then again, I mean, this latitudinal dependence in the sense that this instability is stronger at the poles compared to the equator, that is still valid, even if we have done that trick here. Okay. And another interesting thing is I was talking about this pumping. Oh, yes. So should I? Maybe I will go with this. Because that summary is also here. So there are some things that we found out from this study, and that was this dependence of growth rate and the twist on the Roberts number. So higher the higher or the efficient the heat conductivity is, the growth rate and the twist of the tubes that are produced is higher. And then we have reconstructed the turbulent EMF using QKTF, and then we found that you have to use a convolution rather than a simple multiplication to get the actual EMF. And then this sign of the turbulent pumping velocity actually depends on the scale of the magnetic field, which was the last slide. So if you have a magnetic field which is on the scale of the box, it is actually pumped away from the layer. Whereas if you have magnetic fields which are of the scale of that layer, they are pumped into the layer. So we don't know how that affects. And then the turbulent diffusivity in the magnetic layer also increases to something like 50 times the molecular value. This is interesting because magnetic fields are known to suppress magnetic diffusivity, whereas here that is not the case. But that is simply because these diffusivities or this turbulence is actually being generated due to the magnetic field. So if you increase the source of this turbulence, then obviously the diffusion will also increase. And then other thing is this anti-quenching of the transport tensors. They increase with the initial magnetic field. And then we also studied this latitudinal dependence of alpha and beta. And then I just have this slide for the symmetry breaking thing, which is what happens to this instability in absence of rotation. So this was actually also studied by Fan in 2001, but fortunately she didn't look at this problem in this perspective. And then
she didn't work in astrobiology.
Yeah, that's right. That is true. So what determines the sign of the final alpha effect? So we were having the same problem that we were having in the equator about which sign of the eddies to take. And then we found that for depending on what sign of kinetic helicity you put, the alpha effect chooses that particular sign. So is it a spontaneous parity breaking, or is it antagonism where there are two different helicities or two different helical modes, one is suppressing the other, or is it related to first order phase transitions? So I think Axel can later talk about this and Fubo can talk about it. Huh?
They're all the same.
All the same.
They are first order transitions and that causes.
But second order is
Not first order, because it was first derivative of free energy, right?
It's another Hitchcock application.
Then it is on the derivative order of the derivative.
the magnetic transition is second order.
Yeah, I think you're right.
But it is the first derivative of the free energy.
Yeah, thanks. We are going to be the common doesn't be more than, it shouldn't be more than much more than Chatterjee.
I didn't understand what is the direction of the pumping and what it does with the magnetic field.
Yeah, because that depends actually on the sign, on the scale of the magnetic field. So I mean, we calculated this alpha at different k's. You remember?
Yeah.
So if you take this gamma at a lower k, and then you take this gamma at a higher k, they have opposite signs. So what does this mean? I mean, the gamma at lower k will act on magnetic field which are lower k, which is large scale. And the gamma at higher k will work on magnetic fields which is small scale. So
And it have
because
okay.
it's a convolution.
But it is pushing or transporting the magnetic field in what direction?
Depending on the scale of the magnetic field.
Well, okay, so the large scale magnetic field are transported where?
Away from the layer.
So latitudinal in the x direction.
No, Z.
Upwards or inwards?
Upwards.
So this
or away from the layer. So there is a horizontal layer.
Yes.
Away from the layer is away from the layer.
In upwards. So this is not the velocity of the magnetic flux tube, in other words?
No, pumping is not really the velocity of the tubes, right?
Why not?
Because the tubes are always going. The tubes are always going upwards, but that
how
At a,
first you
at a smaller scale, the velocity is down.
I was looking into this.
Yeah, but the tubes are larger scale, large scale.
Acceleration different.
Less than 10 meters.
I don't know and what to call large
Yes,
scale and what
that's
to call
20
small scale.
plus minus.
Yeah.
Still.
No, that's not so few.